be talking about ESP, so electric submersible pump, in steam-assisted gravity drainage. So basically, I'm going to explain how the oil is being produced to surface using a pump, electric pump. So what we have here, we have a production well. So this will be an infill producer, and we have an injection well. And so through the injection, we inject the steam and we grow the chamber. But that steam is condensing after it transfers its heat, and the water is being produced downwards towards the or infill or the production well. Now, in each one of the producers, the wells that sit at the bottom, there will be a pump. And typically, what they do right now in the SAGD world, this pump is called an electric submersible pump. So, an electric submersible pump will be kind of a really key component, and it will use a concept of artificial lift. And the way it really works is that artificial lift is really uses electric motor to drive multi-stage centrifugal pump to lift resources from the well, right? So you have a lot of drainage there, like liquids. You have water, you have oil, you have gas that maybe short circuits and comes to the well, and some gas that comes out of the solution is part of the overall emulsion. So the pumps are used to extract the bitumen water mixtures from the production well. And after everything has been mobilized by the injection of steam, again, we cannot really produce the oil because it's very viscous. It's as viscous as a hockey puck when it sits at very high pressure. And so the heat transfer really mobilizes that oil, and the soup is being produced through the electric submersible pump. These pumps are favored for their ability to handle really high production rates. Those operating conditions could be very difficult. For example, very high pressures, very high temperatures, multi-phase flows, as mentioned. But those are very typical in the SAGD environment, right? So let's talk about some of the advantages and maybe some of the challenges associated with the pumps, and maybe talk about some ways to maybe optimize, pump utilization. So first of all, the advantages, as I mentioned, is high production rates. So you can handle very large volume of fluid produced and very kind of multi liquid partitioning kind of production. So bitumen, obviously, it's a kind of hydrocarbon soup. There are many different carbon components, hydrocarbon components within the phase. And obviously, we have the aqueous phase. Now, the aqueous phase, the water phase, will be kind of include some of the steam that will be maybe in gaseous phase. And so the pump should be able to be kind of sensitive to it and not necessarily fail right away. The harsh conditions, we talked about it. So the pump could be operating at 250 degrees Celsius, 275. So, and the very high pressures, right? So, and then you have the concept of basically sand that's getting produced as well. And so this is something that's really important to be mindful of as part of the operation. And you have really wide range of operating ranges. You need across the flow rates, as I mentioned, and the partitionings. And so the pump should be able to account for that. Now, the pump also should be able to be adjustable in the sense where maybe there are some issues at the plant where you process the oil and process the water. So you need to be able to adjust or tune down the speed of the pump. And so it usually typically it measured in hertz. And so then the operation people will, engineers or operators will adjust the pump speed, maybe to produce more or less liquid, which is very beneficial, not from also kind of maintenance operating perspective, but also from maybe economic perspective. Maybe oil prices are low in a certain period of time, and so there is kind of incentive maybe to slow down to pump speed and kind of increase the subcool in a sense. Well, what are some of the challenges? As mentioned, some of the advantages to high operating conditions and fluid partitioning are also the challenges, right? You operate in very extreme temperatures, and there are many components to the ESP pump, so electric submersible pump, and so those components could fail potentially, and then you will require replacement of the pump. Obviously, things you have flow like water, you flow hydrocarbons, some sand, right? So you need a very robust design and really kind of being protective when it comes to things like corrosion and maybe like solid particles that flow through like sand. And gas handling, which is a big challenge in SAGD, for example. And one thing I could tell you that I've seen a lot of examples of that in my personal career, where the gas that, or you can inject the non-condensable gas to maintain the bottom hole pressure in the reservoir, or maybe gas is coming out of the solution that's being embedded in the oleic phase, and then now the pump requires to kind of not only to survive in that kind of operational conditions, but also being able to handle variation of those different gas flows through the pump, where geology also plays an important role because heterogeneity and ununiform kind of non-homogeneous geology could also create an environment where gas could be short circuiting and coming down to the pump. So let's talk about some of the potential solutions to mitigate the potential pump issues. And today we're going to be talking a little bit more specifically on one solution that I have experience on. In this is basically like how do you avoid gas lock-in and problems to reduce, improve efficiency, reduce costs, and things like that. Because once you have significant gas coming through the pump, it kind of it could be challenged, right? Especially with the flow through the pump. So yeah, so I'm going to be discussing like some innovative method to improve heavy oil production, specifically addressing some of the common challenges in SAGD, right? That and I alluded to that, which is gas interference in electric submersible pumps, and for short, we'll say ESP. So just to kind of give you a broader background, maybe to SAGD and kind of part of the challenge here, you could have heavy oil and bitumen, right? So which found in reservoirs like Athabasca oil sands. So those, as I mentioned, are very highly viscous, and really, like at the initial stages, they exceed 1 million centipoise, 5 million centipoise, so very very viscous components. And so one thing to be mindful of is that it's hard as a hockey puck. And SAGD is really widely used technique to address this, where you inject steam through the injection well and produce, basically transfer the heat inside the chambers, and then produce the condensed water with the oil and the gas that's come out of the oil, because it's all hydrocarbons, right? So there's lots of methane in there to produce through the pump. So significant issue could happen when you inject things like maybe solvents or non-condensable gases, because by definition in the injector you already inject something that's very gaseous, and that gaseous component could create kind of different, develop the chambers in various ways, but also it could short circuit to the production well. And this could result in gas lock-in, essentially, where gas accumulation really disrupts the pump's ability to handle liquid emulsion. So the idea is to produce the oil, right? But the pump could be challenged to fill out of gas coming in, and this could result in reduced oil production rates and increased operation cost. So some solutions will be like increasing maybe steam injection to kind of reduce, you know, reduce the gaseous components, and in fact like increase the maybe the liquid more, the liquid level in the reservoir. But this is very inefficient because now your steam to oil ratio could increase. And there are some other ways where you could mitigate the gas interference by strategically controlling where you inject basically the gaseous components along the well. And again, you would inject those components because you will need to pressurize the reservoir and maybe displace the steam to reduce the steam to oil ratio. So it really requires like an ability to decide where do I want to inject and how would I do that, right? And so when gas lock-in detected, you can operate in a sense by injecting the NCG or solvent in different other sections of the pipe. So this could be one of the solutions. And the distance from ESP will be very beneficial, right? Because if you inject next to the pump, then the gas could short circuit. But if you inject kind of far away from the pump, then the gas will have a longer route to get to the pump. So, and then it will go inside the steam chamber and continue kind of that recovery scheme, which not only economically beneficial, but also from environmental performance. This will improve chamber development. This requires kind of like concept of a little bit dynamic adjustment when it comes to the completions that being utilized. And that's kind of basically the solution, is that if you able to have completions where you could be injecting in the toe sections of the reservoir and not towards the heel, then you position yourself for success to avoid that potential short circuiting, right? So this could be one of the solutions. So in conclusion, basically, we talked about USP. We introduced the concept of how oil is being produced in SAGD environment, how to maintain efficiency. We talked about some innovations associated with the electric submersible pumps, which utilizes artificial lift technologies, right? And some injection kind of strategy to solve the gas lock-in problem and improve the recovery scheme. So thank you so much, and I'll see you in the next video.